Now let us understand the customer behavior in a queue. The customers can behave in these four ways. They can do bulking, reneging, collusion, or jockeying. They can be involved in bulking, reneging, collusion, or jockeying. What is bulking? Bulking is a situation when customers decide not to join the queue if it is too long. Now suppose you go to a system and you see that the line is too long. You estimate that you do not have much time, and if you join a queue, you will be late and you cannot afford to spend that much time in the queue. So you will not join the queue and you will move out. This can also be forced barking. In case of a forced barking, you are not allowed to join the line. Like I have given you the example of the bike mechanic, where there was a restriction on the number of people who can join the line. So if you become the 11th person and there are only the length of the queue is limited to 10, so you will not be allowed. You will be required to leave the system. So you are forced to leave. So it can be forced bulking or it can be unforced bulking. So normally if you go and you estimate on your own that it is going to take a lot of time and I do not have that much time and so I should not join the line, so you are doing bulking. Then the second is reneging. It happens when suppose you went to the system, you uh, join the line, but after some time you realize that it is going to take a lot of time and maybe you do not have that much time. So you want to leave and you left the line. So here the customers leave the queue if they have waited too long for service. You go and join the line. You were there in the line for a long time, and then you feel that it is taking too much time, it's getting so much late, and you cannot afford to wait for long, and then you leave the line uh, after waiting for a long time, and you leave without getting the service. The third case is collusion. Here the customers collaborate with one another, like you might have seen at the cinema counters or sometimes in the railway reservation counter also. The people, they do collaboration. Uh, one of the person takes tickets for many persons. They collaborate with each other and one of them decides to take the ticket for many persons. They collect the money, they pull the money, and one person as a representative of 3 4 persons can join the line, and then he or she might purchase the ticket and then give the ticket to others by taking the money from them, or already he or she has taken the money and then he will purchase the ticket and give the tickets to the persons who have collaborated with him or her. Then we have jockeying. Here it normally happens that when we enter a system, like suppose a system where there is multiple lines. This happens when there are multiple lines. So what happens when we go to such a system, we try to assess which line is shorter, and we have a tendency of joining the line which is shorter. So suppose we went to Big Bazaar and there are four lines, and we see that in one of the four lines, uh, suppose in one line there are 20 people, in the other there are 19 people, and in one of them there is 21 persons, and in one of the lines there is only 17 persons. So what the new person who has come to the system will do, he will join the smallest line. He will go and join the line which has only 17 persons in it, and after some time he realized that one of the lines is moving faster, and uh, his line is not moving faster. So he may decide to quit his line and join the other line which is moving faster. So this behavior is called jockeying. When he switch from one queue to other queue with a thinking that they will get served faster by doing so. So here the customers switch between queues if they think they will get served faster by. Now, how do we analyze the queuing situation? We are typically interested in the questions which relate to the measurement of the performance of the system. And how do we measure the performance of the system? We measure the performance of the system in terms of these three types of values: input value, intermediate values, and output values. So input values that include lambda, which is the arrival rate. We have already seen that we assume that the arrival follows a Poisson distribution with lambda per hour. The rate of arrival is lambda per hour. And then the service rate, the service time is exponentially distributed, and the mean service rate is mu per hour. And rho, which is the ratio of lambda and mu, is called the utilization factor or traffic intensity also. So we also are interested in knowing rho, and here the lambda upon mu should be less than 1, and C is the number of servers. We are also interested in knowing the number of servers. So these are the input values of the queuing model. Then there are certain intermediate values, like the probability that there are 0 persons in the system. We are interested in finding the probability of a particular number of persons in the system, and these are the formula for calculating the particular number of persons in the system. Like probability that there are 0 persons in the system is denoted by 1 minus rho. Now here one thing is to be noticed, that if we know these things, lambda and mu, if we are knowing the value of lambda and mu, we can calculate the value of rho, and only these three things are sufficient to analyze the performance of any queuing system. On the basis of these three things, we can calculate everything else. We can calculate the probability of the number of persons in the system, like probability of 0 persons in the system, probability of 1 person in the system, probability of 2 persons in the system, or probability of 3 persons, probability of n persons, and so on. So these are the formula. P naught is equal to 1 minus rho, and P1 is equal to rho into P naught, which is rho into 1 minus rho, and rho square P naught, P2 is rho square P naught, which is equal to rho square into 1 minus rho, and so on. Pn is equal to rho to the power n into P naught, which is equal to rho to the power n into 1 minus rho. Here, length of the system, these are the output values. Length of the system means number of people in the system. It is ls and get denoted by ls, and the formula of ls is rho into 1 minus rho. Then length of the queue, number of persons in the queue, it is rho square into 1 minus rho, which is equal to ls is equal to lq plus rho also. And waiting time of the system means ls divided by rho, ls divided by lambda, which is also ls is equal to lambda into ws. Waiting time of the queue is wq, and lq divided by lambda, also lq is equal to lambda into wq. So these are the formula which we need to remember while solving the problems related to. Now for representing the queuing models, we use Kenda's notation. A particular notation is used. This is a standard notation to classify queuing system, and this notation is in this form: A, B, C, D, E, and F, where A represents the probability distribution for arrival process, what is the probability distribution followed in the arrival process. B represents the probability distribution for the service process. C represents the number of channels or servers. D represents the queue length. E represents the population length, and F represents the queue discipline. Now we can classify the queuing models into different types. However, we have to study only the first model, MM1 infinity infinity FCFS. This means this M represents the probability distribution for arrival process, which is a Poisson distribution in our case. This second M, this represents the probability distribution for the service process. Here it is exponential distribution. This one is the number of channels or servers, single server. This infinity represents the queue length, so infinite queue length. This infinity represents the population, that means infinite population. FCSS is the queue discipline, so customers are served in first come first serve basis. Then second is MM1 NFCSS. So this is uh, Poisson distribution, exponential distribution, single server, finite queue length, and first come first serve. Poisson distribution, exponential distribution, multiple server. S means multiple server, infinite queue length, FCFS, first come first serve. Poisson distribution, exponential distribution, multiple server, finite queue length, and first come first serve. So these are the different classification of queuing models. We will be discussing the MM1 infinity infinity FCFS model. Here this M represents the Poisson distribution. The second M represents the exponential distribution. The first M represents arrival, which follows Poisson distribution. Second M denotes the service rate, which is following exponential distribution, and the service rate is mu per hour. This one represents the number of servers. So we'll be discussing this single server model. Then this first infinite represents the queue length, that is infinite queue length. The second infinite represents the infinite population, and FCSS represents the service discipline, which is first come first serve. Here we use M because the system follows memoryless property. What does memoryless property mean? It means that the system does not have any memory. That means it does not take into account the earlier states of the system in order to define the present state of the system. So the system does not remember what has happened, and what is happening in the past has no relation with what has happened in past. So the system does not have memory, and that is why it is this M symbol is used here. First M denotes the arrival, which follows Poisson distribution. Second M denotes the service, which happens at the rate of mu per hour, and it follows exponential distribution. One denotes server, single server model. First infinite denotes the queue length. The second infinite denotes the infinite population. The third, then the FCFS model means the service discipline. So we will be basically in our syllabus we have to discuss about MMN, MM1 infinity FCFS model. So we shall be taking up the numericals in the next video.